Hey guys, and welcome to a brand new PSP GPU tutorial. So in this tutorial series, we'll be covering how to use the PSP GPU, also known as sceGu, which stands for Sony Computer Entertainment Graphics Utility. This will basically allow you to make any 2D or 3D applications on the PlayStation Portable, and overall, it will give you a better understanding of how the PSP's GPU and graphics system works. In this tutorial, we'll be walking through the setup for the boilerplate code. So this will be setting up a rendering context, which you can then use to run further rendering commands. In the future tutorials, we'll be using a wrapper that I've made called GU2GL, which will also be linked and will be showcased at the end, which will also handle some of the code that we set up today. If you want to follow along with the GL style of sort of programming and the way that it looks, it might be a better idea, and it will also be more comfortable for those of you who are used to to desktop OpenGL. This tutorial is made for intermediate programmers who are decent at C, C++, or who can convert it into Zig and Rust. It's written in Common C, so it should be very easy to translate over the code. It's also recommended that you have at least a decent understanding of how computer graphics works in general. If you go ahead and look here, we have some pretty simple boilerplate code. Pretty much, basically, we have our callbacks.h, which you'll be familiar with if you follow the other PSP tutorial series. Pretty much it just gives us this setup callbacks function. And in this tutorial, we'll be including the graphics libraries, which includes PSP Display, PSP GU, and PSP GUM, which is graphics utility for matrices. Of course, we'll be setting up our module info here, and then creating a running variable. This would be helpful for more established programs, but for here, it's just used to create an infinite loop. We're going to run the setup callbacks function, which sets up the home button callback so that you can exit the game. And then if you ever get out of this main loop, it will just terminate the application. First things first, we're going to go ahead and define some of the variables in the scope. I had this earlier here, and this is just some defines for the PSP width and height. So there's this PSP buffer width, and then PSP screen width and screen height. The screen width is 480 and the screen height is 272, which matches the physical layout of the PSP itself. And the PSP buffer width is set to 512. The reason that the PSP buffer width is set to 512 is that buffers in the graphics engine, or the GE, basically are required to be power of 2. This applies for pretty much any texture that you want to output. So the PSP buffer width here is going to be 512 because the nearest power of 2 to 480 is 512. As a clarification, the nearest power of 2 means that the nearest greater power of 2. So for example, if I had a 129 by 129 texture, I would actually need a 256 by 256 buffer, because that you need to be able to at least fit the texture inside of that. Or you could cut off the pixels. That's also another solution. The next big thing that we will be defining here is the GE list. The GE list is basically a big buffer in memory that we use in order to actually communicate with the GPU. Basically, what this entire list is, it's a place where essentially all of the GPU commands coming out of sceGu are basically being placed into before they get sent over to the actual GE or graphics engine to render everything out. The list is basically started off at some point using sceGu start, and this list will basically be filled up with commands as you write them. So if I enable something, that gets written to this list, and this list is in order, obviously. So every command is written one after the other. This list is then basically executed by the GE. There are some specialty functions in GU for loading up lists and doing this as well. This can be a helpful optimization for the PSP if you ever have something that's always being displayed to the screen, such as a HUD, where you only need to build the list one time and then you can pass it back as many times as you want. For the most simple application here, we're just going to be rewriting this list every frame. Now, let's create some functions here that will help us with VRAM. So the PSP's VRAM system is a separate area of memory between 2 megabytes or 4 megabytes, depending on your actual model. You can enable the 4 megabytes on the PSP 2000 Plus models with sceGu EDRAM set size, which is not in this older version of the toolchain that I have here on Windows, but it is in the current version, and you would just set the size to be 4 megabytes. So for our VRAM management functions, first off, we're going to create a function here called getMemorySize. So static unsigned integer get memory size with an unsigned integer width and an unsigned integer for the height and an unsigned integer for the pixel mode, which is PSM. Basically, then we can calculate this getMemorySize function. All it does is that it's going to be calculating the required bytes that you would need for an actual VRAM buffer. So this basically is just calculating how many megabytes we need. So the formula for that is basically to do width times height and then times the bytes per pixel. In this case, bytes per pixel, we're going to use a switch statement and use PSM to calculate that. So if we switch based on the pixel mode that we get assigned here. So for the first one is PSM T4. And basically T4 here is describing that there are four color values, R, G, B, and A, so red, green, blue, and alpha. Alpha determines transparency. So in T4, basically, that's 1 bit per every member of a pixel. So 4 bits per pixel, which means 2 pixels per byte. So this will be size divided by 2. This also has a side effect of being black and white. T8, on the other hand, is grayscale, and you have 2 bits per color channel, which will mean that per each byte you will have the entire per each byte you will have basically a 4, which basically means per each byte you would have a pixel, and that pixel has 4 shades for every color. Then we have some more formats here. 5650. We have 5551. We have 4444. And we have T16. Basically, all of these are specifying the number of bits per each color channel. So this one has no alpha, this one does have alpha, this one has 4 bits allocated to each, and then T16 I believe is also grayscaled. I'm not quite certain on that. Basically this is size times 2 because we will need 2 bytes per each pixel. And then finally we have PSM 8888 and T32. And this will be size times 4 because you will have 1 byte per each color channel of a pixel. And then, as a good safety measure, just in case, default return 0. So this won't actually create a buffer if you don't pass in one of these values. So, we now have a way to get the size of a buffer. Now, let's actually create the code that creates a buffer. So we'll have a void pointer, which will be the pointer to our buffer, and get static VRAM texture same arguments as before, unsigned integer width, unsigned integer height, and unsigned integer pixel select mode. And basically we will have a static unsigned integer here called the static offset, and that will be initialized to 0. And basically what this is that every time you request a new static VRAM texture, it will increase this offset. So we will create an unsigned integer memory size is equal to get memory size of width height PSM. So now that we have that, we can create a void pointer, which will be our result, which will use void pointer, and it will just be based on the static offset. Now this returns basically a VRAM, this should be a VRAM buffer, my bad. But basically this will return the VRAM buffer relative to 0. Now, this is needed for some of the sceGu operations because these will be GPU side operations, so 0 is actually the start of VRAM for the GPU. So return. So we'll have static offset plus equals memory size, and we'll return our results. Now for the actual texture, so the stuff that we can set from our main memory here, get static VRAM texture, which will have the exact same arguments. We can then do void pointer result is equal to get static VRAM buffer of unsigned, of width, height, and then PSM. And then we will return a actual void pointer here, where we go ahead and take number 1. We're going to take our results, and we will cast this to be an unsigned integer. And then basically we'll take result, and then we'll add it to sceGEDRAM get address. There's also a void pointer, so we'll cast that to unsigned integer. And basically what this does is this ends up taking this this buffer that we created, which starts at 0, and then setting it to the beginning of where VRAM is. This will be for our CPU for setting textures. So now we have these basic VRAM textures. Now that we have all of this code here, why do we need this? And the answer will become pretty apparent when we start initializing graphics. So let's start with that. Init graphics. So we're going to create a void pointer. This will be our frame buffer pointer 0. And we'll take a get static VRAM buffer. And this will be PSP buffer width, PSP screen height, and then PSM 8888. You can set this to different texture formats. Just make sure that when you're doing FBP1, so this is frame buffer pointer 1, this one will also have to have the exact same arguments here. And frame buffer pointer 0 is going to be our draw buffer, and then our display buffer is frame buffer pointer 1. These buffers will get swapped internally, but they have to be the same, otherwise it won't switch correctly. And then we'll have our Z buffer pointer, which will be get static VRAM buffer, and then this will be buffer width, the screen height, and then this will be PSM 4444. You actually don't need to have the same level of data there because the Z buffer does not record values in color. So now let's call sceGu init. Cool, we initialize the library. That's it, right? No, wrong, of course not. So first things we're gonna do is start our list. So the type is GU direct, and we'll start up the list. Why do we need to start the list? Well, we need to start the list in order for the commands that we're about to do to actually be recorded and then sent to the GE, the graphics engine, to actually initialize it and set up all this data. So we're going to do sceGu draw buffer GU PSM 8888 because that's the format that we're using. And then this will be frame buffer pointer 0, and we need to know the buffer width, which is the PSP buffer width. And then we can do the same thing, but we can do it for the display buffer. Now the display buffer needs the size of the screen, so you use PSP screen width and PSP screen height. And of course it still needs frame buffer pointer 1, so this will be our other buffer. And what this does is it sets up double buffered rendering. So basically the display buffer is whatever is going to be on screen, and then the draw buffer is what we're going to be currently drawing to. By having these two things, we can actually prevent a lot of visual artifacting that would occur if we kept trying to write to the same buffer at the same time that we're trying to display it. And then of course we also need to set up the depth buffer. So we can set ZBP, which is our depth buffer pointer, or Z buffer pointer, and then the buffer width. That way that if you want depth testing, so 3D stuff a lot, and then sometimes 2D if you want to do sorting, that will work as well. So this next part's a little hard to explain, but essentially the PSP has its own sort of virtual coordinate space, and basically what we want to do is that we want to center it. So the virtual coordinate space is 4096 by 4096, so we go 2048, and then we have to center it, so it's got to be the screen width divided by 2, and then the same thing has to happen here, 2048 minus PSP screen height divided by 2. The other one will be sceGu viewport, 2048, 2048, and PSP screen width and screen height. Whoops, 2048. There we go. And this basically just sets up that we're going to be drawing in the middle of our coordinate space, and this is where we're going to draw it to. I hope that makes sense. It's not really a relevant detail for anything else that you're going to be doing, so it doesn't matter too much. So the next thing we're going to do is sceGu depth range, which has basically the near plane and the far plane, and this is based on the actual depth buffer itself. The near plane is going to be 65535, which is the maximum for a 16-bit number, and then this will be 0 for the far plane. Now, as that doesn't really make sense, right? Because far being 0 and near being super far away doesn't really make sense, right? But what actually ends up happening is that the PSP has an inverted depth buffer, so like everything that is nearest is actually furthest away, and everything that's furthest is the nearest. It's kind of weird, but basically you have to set it in reverse order of what it would seem like. We're also going to do an sceGu scissor test. And basically what this is going to do is we'll scissor the entire screen so that everything is going to be basically wrapped just to a specific area. And what I mean by this is that essentially we have this buffer width that's buffer of 512, and it will try to render outside to that. So we want to make sure that we're only rendering within the 480 by 272 area. And of course, to use sceGu scissor, we need to do sceGu enable GU scissor test. The other thing we can set here is sceGu depth func. So this is the depth testing function. Pretty much, it's pretty much the opposite of the way that the desktops So when we're setting the sceGu depth function, the depth function is actually the reverse of what it is in normal OpenGL. Normal OpenGL, you use GU_L equal, but because it's inverted, we have to use GU_G equal. So we have to set it like that. Also, we'll enable GU depth testing. This allows us to have proper depth effects, so things that are further away from you are correctly clipped. The next few functions are pretty much just settings, so we'll do sceGu front face and GU_CW for that. And what this means is that basically whatever the front face will be wound in a clockwise order. Basically, winding has to do with the direction in which you specify individual points of a vertex, and the way that you specify that creates a normal plane. If you have a triangle, for example, it has a normal plane that points in a direction. Depending on which direction it's pointing, then based on its winding order is how you figure out the normal and then whether or not to call the backface of that. This is kind of complicated and it's a little bit outside of the scope of this tutorial, but it is very important that you have the correct winding order. Alongside this, we'll be enabling GU call face. And what GU call face does is it performs the backface calling based on whatever front face is. So this will be preventing us from drawing planes that essentially face away from us. The other thing we can do here is we'll set sceGu shade model to GU smooth, and the smooth shading model is basically garage shading, which means that it's per vertex shading. It's not per pixel, it's per vertex, and this will look a lot better than GU flat shading, especially for things such as colors. If you have a bunch of different colors on different vertices, it will actually end up mixing together as a result of garage shading, whereas flat shading would have each face be its own different color. Another two settings that we'll be enabling is GU texture 2D. So this will allow us to have textured objects. And the other one will be GU clip planes, which basically means that geometry that gets outside of a set area will be clipped out of existence, so you don't have to render it. Now, we have basically all of the stuff that we need to have set up. So then we're going to end up finishing the list that we started earlier. And we're going to call synchronize, and this will basically wait for the GPU to finish initializing stuff. It'd be very nice if your GPU was finished before you sent it another list of things to do. This basically will end up halting you on the CPU side though. Next thing we'll do is we'll wait for a vblank start, and basically this function waits until the next available time to get a vsync frame through. We'll also enable the display as well, so that just to make sure that your display, it will be displaying whatever you set up. Now, before we can go ahead and actually draw stuff to the screen, we'll need a couple more things. First off, we'll have a function here that terminates graphics, and that's pretty simple as compared to our entire initialization function here. Term graphics doesn't take that much to do. The other thing will be starting every frame. So whenever you want to start a frame, you have to call sceGu start to a list so that you can start recording data. And if you want to end a frame, you have to do those things that I just told you about, which is finish it. You have to do a synchronization. In this case, we'll wait for the GPU to actually finish drawing. And then we'll do display wait vblank start. Now, there is another way that you can set this up in order to have it so that the GE will notify, or GU will notify you when the actual drawing is done, and then you can take actions based on that. Same thing with waiting for a vblank start. You can do this asynchronously as well. And then, of course, we'll do sceGu swap buffers. And sceGu swap buffers here is actually incredibly important because what it does is it swaps the display buffer that we set up with the draw buffer. So whatever you just finished drawing over here with the GPU is now going to actually be displayed to your screen at the start of the VBlank. If you didn't do this, basically you would end up having no graphical result either. So let's actually use this code in practice now. So we'll use init graphics. And then we'll have terminate graphics at the end of our application. And then while we're running, we're going to do starting a frame. Then we'll end the frame. Wait for the color to actually fix itself. Maybe. Well, that's interesting. And then we'll have sceGu clear color with 0x ff00ff00. And what this order is that this is in... Can I get a better color? Hold on. Alright, cool. It's not garish yellow anymore. And basically what we have here is sceGu clear color. And this is 0xf0ff00. So basically this is actually specified in RGBA values. So this would be your first 0 to 255 for red, 0 to 255 for green, 0 to 255 for blue, and 0 to 255 for alpha. However, because we're trying to express this as a single integer, we actually do it in the reverse order, so it's actually A, B, G, R. So in this color code, we have alpha equals 255, blue equals 0, green equals 255, and red equals 0. So it's a little bit reversed in this code. There's also a function, if I can pull it up, called GU_color. It's not this. So we have color macros. So this one, for example, this converts 0 to 1 values in RGBA to this code. You also have RGBA here, which is 0 to 255, ARGB and ABGR, which do essentially the same things as well. And then we'll call sceGu clear with a GU color buffer bit. So this will actually color the buffer. So this will actually clear the color buffer of your application, so you can actually see the color. Calling sceGu clear is pretty important for basically just resetting your buffer and getting ready to draw the next thing. Ideally, we also include GU depth buffer bit here to clear the depth of the application as well. So we'll change to our context tutorial. Then we can run make. Cool, everything works. And then if I run eboot.pbp, we can see that our screen colors clears to the green color that we set earlier. So congratulations, you've just made your first sceGu program. Now, if you notice something here, a lot of this code that you're actually running looks very similar to OpenGL. And this is the reason I created a wrapper called GU2GL. And what it does is that it essentially converts all of the GU stuff to actual OpenGL, to OpenGL-like functions. It also defines some very simple things here, such as GU2GL init, terminate, start a frame, swap buffers, and the VRAM texture and VRAM buffer things that we had before. And as you can see, it's converting GL enable to sceGu enable and all of the main things here. We also have an implementation that sets up all of the things that you want to do as well. So actually, we can make this example a lot simpler with GU2GL. And you'll need to define this implementation thing in at least one of your files in order for you to actually be able to use the library. So, cool. We got that working. We don't need this. We still need the GE list. We don't need pretty much any of this. And then we can do GU2GL init with the list. And then GU2GL term. And then we have GU2GL start frame. And we need the list. And this second thing is whether or not this frame will be used for PSP dialog. Unless you're messing with sce utility or the on-screen keyboard, you will pretty much always set this to false. And then the other thing here will be GU2GL swap buffers. And the first argument is whether you want vsync. Usually you do. GL true, and then GL false for the dialog again. Second argument is dialog. These two should always match. And then basically, whether or not you switch on vsync is usually, if you want to actually use the application, it's a better idea to have vsync on, unless you can just sustain 60 FPS. And then you can turn off vsync if you're going to be doing stuff like performance testing and seeing absolutely what your application can do. The other changes here will be GL clear color. Oops, GL clear color. It's still the same format here. And then GL clear, which will be GL color buffer bit and GL depth buffer bit. And if you're an OpenGL programmer, this looks very familiar to you now at this point, and you can probably get a pretty good idea of what's going on. Still recommend watching the next tutorial, because there are some differences, especially with GL draw elements, or sceGu draw arrays. And if we go ahead and make this, and run the eboot, you'll see it does the exact same thing. So congratulations if you made it to the end of this tutorial. You've officially written your first graphics API program on the PSP, and in the next tutorial we'll be covering drawing objects to the screen, specifically drawing a triangle, a colored triangle. So thank you guys for watching, and have a great day.